Thank you. I can't overstate what an honor it is to come and speak to you and be part of this community. It was a community I fell into, and I have fallen in love. So I'm a leukodystrophy doctor, which means I care for children that have genetic disorders that affect the myelin, or the protective fatty wrapping around neurons, things like adrenoleukodystrophy, metachromatic leukodystrophy. It's a world where we are moving very quickly into therapy development, and we currently have one of the new gene therapies is for leukodystrophy, and one that we anticipate soon because it was approved in Europe. So it is a place where we have a lot of forward momentum, and I'm excited today to kind of talk about that momentum we have in the leukodystrophy world, because I think many of the lessons we have learned and much of the hope we have gathered will apply to this community as well. I was promised there is a clicker. Can someone show me how to advance? This, I think, just started off a detonator. I have no idea. There you go. Just hit the yes. Perfect. So as part of my work at the Children's Hospital of Philadelphia, I do have several disclosures I wanted to talk about. We work really closely with industry partners because I think they're one of our stakeholders to be able to take rare diseases into therapies. I work with Orchard, Takeda, Biogen, both for research and as a consultant. For some of these companies, I run their non-concurrent natural history control. I have several forms of NIH funding, as well as several forms of advocacy group funding, including the Don't Forget Morgan Foundation, who's funding our natural history study on BPAN. So what is a rare disease? Interestingly, it was actually defined by what is not multiple sclerosis. So they took the rates of what MS was, and then they defined rare as everything that's not MS. They did not want MS as part of their club. It's a club that has over 7,000 rare diseases. And individually, by definition, each one of them is rare. But collectively, we have a really strong voice. It's 1 in 10 people are affected by rare disease. Now, these are of variable severity, variable how they affect people, but 1 in 10. That means we have a lot of power when we bring our voices together. Unfortunately, the vast majority of these don't have treatments, right? And so we have a lot of work to do in the coming years as we take our rare diseases and we start to move them into the realm of treatments. It is a really exciting call to arms I have for you guys, but we have a lot of work to do to be ready, but we're gonna get there. In brief, I'm gonna just talk about what it means to be ready for a clinical trial. We have to know what cells are affected. So in the brain, there are lots of different cells. And depending on which cells are the ones that are driving the disease, we need a different type of treatment in order to reach those cells. We need to even sometimes know what part of the cell or organelle within the cell is affected, because again, that therapeutic approach varies wildly. We have oral medications, we have infusions, we have gene therapy. There are many different ways we can help children with rare diseases. What I spend most of my research time doing is looking at clinical trial development and what pieces are we missing so that as the basic scientists are developing a treatment, we are ready to roll the moment that that product is ready. I study a lot of rare diseases looking at what happens very early in the disease course, so I can identify what helps me predict what's going to happen in the next 2, 3, 5 years. This is really important for a clinical trial because in rare diseases, thankfully, we're moving away from the concept of placebo control. A placebo is when a child or a family member thinks that they're receiving a medication, but they're not. They're receiving a sugar pill or just a poke. In a rare disease that is progressive, it's not acceptable. And so we need to come up with clever ways to understand if a treatment has potentially worked by using creative methods like non-concurrent controls, meaning we can use patients that were part of a natural history study to compare them in the future to those that are treated. I think it's also important to identify what's the most important outcome. And here, this is where the families are the most important thing. You get to tell us what's important. And then I can help work with you to decide, well, what are the best ways we can measure this, right? Because we have lots and lots of tools, but very few of them have been validated in our population. So we need to ask you, well, what's important to you? Would a change in walking or sleep or seizures be something that's meaningful? Because maybe that should be our goal for our clinical trial. And then one thing we also really need, and we talked about this earlier yesterday, was a biomarker. Something that lets us know that the drug is getting to the place we want it to get and is helping the child. This makes clinical trials actually faster and more likely to succeed, right? So having a biomarker is really important, albeit not necessary. And there's a constant push-pull when we are talking about rare diseases and clinical trials in general on generalizability. So you both want to design a clinical trial for as narrow of a view of a population or a group of people as possible, so you can really cleanly tell if it helped or didn't help. But you also still want it to be generalizable, meaning I can expand the potential treatment to children that maybe weren't eligible or weren't part of that original trial. And so I'll just say that this is something, as clinical trialists, we grapple with, really wanting to help as many kids as we possibly can. Because this room is really diverse in background, and I know there are physicians, scientists, people that have honorary degrees because of the journey that their family has been on, and people that are really new to the scientific or medical journey. I'm going to talk a little bit about the background of DNA and RNA, just so everyone can be with us at the same point, and we just start to talk about the really exciting, innovating treatments that are being worked out now for rare diseases. No neurology talk would be complete without a little bit of history. Neurologists are such nerds, and we really love history. So the history of genetics dates back to Gregor Mendel, who started talking about heredity and how things were passed from one pea plant to another. It was about 20 years later we understood the concept of cell division, and it was about 100 years later before we understood the structure of our instruction manual, which is DNA. It's a double helix structure, but it's, of course, not so simple. A double helix structure would be really tangled within our cells, and so it gets more and more twisted and compacted. And depending on how the genes are twisted and compacted within that structure, they may be open in one type of cell and closed in another. And so when we're talking about DNA editing or DNA targeting, we need to make sure that the information we're trying to change in the cell is open and available for changing. This simple process, between taking DNA, which is that instruction manual, into RNA, into a protein, which are the building blocks, is a process called transcription, where the DNA is switched to RNA. That RNA message is then translated into a protein polypeptide, which is formally folded within the cell. When we have a variant in this information code, it changes the DNA, and that DNA message change is changed into the RNA message change, and sometimes can affect the way the protein is folded. And sometimes that change doesn't make a big difference. You know, those are all their benign polymorphisms, which are changes that we all have. It can be a variant of unknown significance, meaning we don't know exactly if this is actually going to cause a disease, or it could just be a normal change. Or it could be a pathogenic change, where we know we've seen other children or people with that same change, and we have seen it cause disease before. So that's our very basic primer on genetics. Hopefully everyone is with me now, because we're going to start to talk about the exciting ways that that information in rare diseases has been changed. There are lots of different approaches, and this is just a kind of a general primer, and we're going to go through each one. One is, if you have a missing piece, usually an enzyme, you can just give it. It doesn't make a sustainable process. If you think about that old Jimmy Carter quote about teaching a village to fish is very different than giving them the fish themselves. This is just giving the fish, right? You can infuse a missing piece. It usually needs to be done with an incredible frequency. For most of the lysosomal storage disorders, where enzyme replacement is an option, it works beautifully. Gaucher, Fabry, several of the mucopolysaccharидoses or MPS disorders, this works great. Sometimes you can give the instruction manual. That's a lot of what gene therapy is, right? You are giving the instructions to cells on how to make the piece that was missing. Metachromatic leukodystrophy has approved gene therapy in Europe, which I'm really excited about. Adrenal leukodystrophy has bone marrow transplant, which actually gives the instruction manuals to the cells that you are adding in. Adrenal leukodystrophy also has gene therapy, which was approved, I believe, in September of this year. SMA, or spinal muscular atrophy, has gene therapy as well. There are also some approaches that change the way your own instructions are carried out. These are things like antisense oligonucleotide therapy, and we'll talk about this more in depth. But things like the Spinraza, the SMA therapy, actually just changes your own instructions. It gives like an addendum on how the body is supposed to read them and make proteins. And then there are other approaches that have been approved that don't fix the instruction manual. They don't change how your protein is being made, but they help with any downstream side effects you're having. So in Friedreich's ataxia, we just had a medication approved that reduces the antioxidant damage that happens from it. So they don't even touch the Friedreich's ataxia gene. They help with the consequences of it. And then there's another disorder called CTX, and we'll talk about that in a little bit more depth, where you aren't able to make one of the pieces and then you just give it. You can supplement it. That one is not FDA approved. And there's also a really exciting new avenue where instead of giving a second copy of the instruction manual, we're just fixing our own cellular instruction manual, and that's called gene editing. And the first gene editing approach was just approved fairly recently for sickle cell disease. And I envision this is probably the way we're going to be moving for rare diseases that are caused by a single gene change. So let's talk in brief about what supplementation therapy is. So that's when you're supposed to take a product and move it from A to B, but you have a block somewhere along the way. And so you just give the product that's missing, right? You don't have any toxic buildups of anything, you're just missing a piece. So in those cases, like in CTX, children and adults have a deficiency of something called CDCA, and that's something you can buy, so we can just give it, right? So in a person with the disease, they're unable to make that final product. They start building up all these toxic byproducts, but it gets even worse because when you are missing the CDCA, it feeds back into the loop, and now you start making even more of these toxic byproducts. So what you can do is you can just supplement the CDCA, and it helps extraordinarily well at blocking the consequences of having this disease. So your instruction manual stays the same, right? You've just kind of short-circuited this pathway. The other way you can do it, as we talked about, is enzyme replacement therapy. So if you're missing an enzyme, enzymes are actually, in general, pretty easy to make in the lab and pretty easy to infuse. So understanding in your disorder exactly what step is missing is inherently just essential for designing the treatment. And there are lots of enzyme disorders where this is really the best approach, although it's not long-term. So let's talk about the innovations behind what's happening among gene therapy and transplant. So for some disorders, and the NBIAs are not within that group, we can actually just use a bone marrow transplant, just like we use for cancer, where we take someone who is unaffected, we harvest their stem cells, and we give them to someone who is affected. And then you form what's called a chimera, which means you have a little bit of your own cells and a little bit of someone else's cells. And those missing cells can make the piece that's missing. This is used in ALD, and I'm going to put a caveat on a little bit in MLD and Krabbe. We think sometimes enzyme deficiencies, treating it works really well because they can actually share the enzyme between cells, and that's something called cross-correction. So what about gene therapy? That's what I think we're really excited about, is gene therapy and gene editing. If I can put it into two broad categories, there's ex vivo and there's in vivo. In ex vivo gene therapy, what you're doing is you're taking your own cells, you are giving the missing piece. Usually you use a virus to carry that information into your cells, and then you give them back to you again. So kind of like a bone marrow transplant, but you're transplanting your own cells after you've given a new instruction manual. An in vivo gene therapy is where you actually take the virus itself and you put it directly into the person, so you don't have that kind of bone marrow transplant step within it. If you think about the viruses that we use in gene therapy, think of them as an envelope with a message that we're sending from one cell to another. So we tend to take out pretty much all the pieces of the virus that make them the virus, but we keep the shell, or the envelope part, which is called the capsid, and we give them the instruction manual that we want, and we take out everything else we possibly can. There have been 4 general classes of viruses that have been studied to be the backbone of this. Lentivirals, and very similarly the retroviral DNA ones, are RNA viruses. And the other form is adenovirus, which is not super hot these days because it causes your body to have a big immune response, because we've all seen adenovirus as the common cold. Most of the big energy is happening around something called adeno-associated viruses. And in the end, I don't know if that's going to be the only approach, but it's kind of the hot one these days. Yesterday, it was mentioned about the Bespoke Gene Therapy Program, which is a collaboration between different investigators studying ultra-rare diseases, the FDA and the NIH, and industry partners all working together to form a more efficient way to do ultra-rare disease gene therapy. And they're all using adenovirus vectors for this one. I think the next wave, though, is not going to be probably viruses. In the future, I think we're going to be looking at things like lipid nanoparticles, which basically have the envelope, but they never came from viruses. And I think the big challenge for this is going to be able to tag these lipid nanoparticles to be able to get into the cell types of where we want the information to go and keep them out of places we don't want them to go. That's a big challenge with gene therapy, particularly your liver. Its job is kind of cleaning up your blood. And so when you infuse a vector into your blood, your virus is going to take up a lot of it and break it down before it can ever send the instruction manuals to the places that we need. And so something like a lipid nanoparticle might allow us to be more efficient and also much more targeted, avoiding potential side effects. So how do we do the genetic manipulation? Well, the basics of it, again, are we take someone that is affected or not affected, harvest their cells, and give that missing piece. We don't call them viruses in this case. Again, we call them vectors because we've taken out most of the virus pieces of them, and then we infuse them back again. And when we call it an autologous stem cell transplant or gene therapy, it's referring to the fact the cells came from the person, they got the vector, they were grown up, and then given back to the patient again. Depending on the disorder that we're talking about, there were lots of different ways to get the gene therapy into you. One of the first gene therapies was built out of my institution at Penn, was actually a genetic disorder of the eye. And so you infuse the gene therapy product into the eye, because that's the only place you want that information to go. If you have a disorder that's affecting your liver, it makes sense to give it by blood. But as we're talking about neurologic disorders, we've had a lot more challenges of getting the information to exactly where we need it to go. And so people have tried the IV approach for gene therapy, and it hasn't worked great. Sometimes it works okay, but oftentimes we run into the problems of all that information that we're trying to send into cells gets sucked up in other places and doesn't make it into the brain. So the next approaches were taken, which was intrathecal. Are there any moms in here that had an epidural when they were giving birth? It's the same thing, right? You do a lumbar puncture, you infuse the gene therapy product through that. And we've started actually to go higher and higher with where we're infusing, because a lot of times we don't care about fixing the spinal cord as much as we care about fixing the brain. And so people have moved into cisterna magna, which you have a big kind of open pool at the back of your head where you can fairly easily inject gene therapy products into it. Intracerebroventricular, you have fluid lakes inside of your brain that you can inject into. An intraparenchymal, which means injecting into the actual brain tissue itself. There are several gene therapy products that are approved for neurologic disorders. There's MLD, as I mentioned, in Europe. That is, again, that ex vivo infusion of the autologous stem cell transplant, and ALD, which uses a similar approach. That I want to point out, though, each one of them has barriers. So in MLD, they are successfully giving gene therapy to pre-symptomatically identified children, but only in a subset. Not every single country has agreed to it, even though the data is there, and many countries are giving it. And it is not yet approved in the United States. And so as we see children affected by MLD, they are crowdsourcing to get enough money to be able to go to Europe to get their treatment. And so I bring this up because just having a product that works, even an approved product that works, doesn't take away all of our barriers as a community. The story with ALD, I think, is even sadder. It was approved in Europe, it is approved in the United States, but insurance companies in the US are paying for it, and in Europe they have decided not to fund it, so little boys identified with ALD in Europe are unable to get the gene therapy product because they have decided en bloc to not allow it. So again, we will not be able to rest on our laurels until we have a product or an intervention that helps children and helps all children, right? We have a lot of barriers to be able to deliver this personalized medicine for rare diseases. In the US, we have a lot of movement for additional gene therapy products, which I think will make our road as a community both easier, we'll be able to learn from their mistakes and from their successes, but also more challenging. As more and more rare diseases have treatments, it's going to be harder and harder to get payers to pay for $3 million per intervention. And so coming up with a more efficient system and also a really strong, loud voice is going to become really important. So I want to share a moment of hope. This is for a disorder called aromatic L amino acid decarboxylase deficiency. This is one of the neurologic disorders. It's a metabolic disease where children don't make dopamine. And because they are missing the instructions on how to make dopamine, their body has horrible dystonias, and the children have difficulty moving. They decided they were going to do a much more targeted intervention for their gene therapy. And I want to share a video. And with the caveat being, the outcomes from this trial were extraordinary. Because of the mechanism, children were able to gain back skills that I don't know we'll see in other disorders. But I want to share that. Oh, how can I share that moment of hope? So this is the child at 2.5.
Go! 加油！
So that was before the gene therapy infusion. This is 1 year afterwards.
他说可以大概承受10公斤啊，对，但是它不算很厚，对，不算很厚。但是我们之前买就是怕丑，所以又要在这一堆人。
他现在站立架站多久？
我都让他至少30分钟。哦，对，
一天30分钟。
没有就一次，大概一天有时候2次，对。然后反正就是最少30。
过去。他现在下盘有比较稳一点点。
我觉得有比之前再好。
对，因为他之前就是有点乱走那种感觉，他现在是稳的。所以平常都有穿矫正鞋。
对。但是还是很奇怪，他穿矫正鞋还是脚跟走。
So that's an example that is just beautiful. It is our aspirational goal with all of these treatments to change the course of disease, to change the destiny of a child. And that is what we're working towards. Not every disease gets there. And it is a really hard, long road, which I know everyone here is very aware of. If you look at the things that have been put forward for diseases, in this case, lysosomal storage diseases, these are all the enzyme replacement and gene therapies that have been in trial, and you compare it to what has been approved, it's really low. So about only 10% of things that are in preclinical development, which means in the lab, actually make it to a therapy that helps someone. And there are lots of barriers to that, right? Sometimes it just doesn't work the same way that we thought. Sometimes we didn't ask the right question in the right way. And so I think as a community, we need to work together, identifying what's meaningful to us as a community. Will help you figure out how to best measure it in a clinical trial, but we'll also put forward many different avenues. It's not trying one thing as a community, it's trying many things as a community. And we need to diversify our portfolio to get success. I'm going to talk about some of the more innovative approaches that are coming along. So again, if we don't change the DNA instruction manual or give another set of instructions, we can actually change how the protein is made. The story of antisense, or RNAi, comes from actually petunias. They noticed that petunias would have these really weird streaks of color within them, and this vibrant blue color was popping out. And it had to do with the petunias actually had something called RNA editing. So again, that's that second step from DNA to RNA. And several Nobel Prizes later, they figured it as actually instruction manuals we all have. It's not to change our color into different petunia colors, but RNA actually is a way our body modulates or changes the DNA instructions, because we're not very good at changing the DNA instructions ourselves, but we can change how that's made. And so we use something called the RISC complex, which goes in, binds our RNA, breaks it, and stops it from being made, right? But what we can do with antisense oligonucleotides is actually use the process that already exists in our body, give that instruction manual to like bind and change how it's being made, and get things like proteins that are made too much and that causes a disease, we can make them make less of them. Or let's say we can make them skip an exon or one of the instruction manuals in order to make a different form that works better. There are some approved therapies, one of which is in the neurology sphere called Spinraza or SMA. And there are several trials ongoing for neurologic diseases, including one for Alexander disease using this antisense technology. These are really good when you have splice variants or overexpressions. They don't work so well when you have something like just a missing piece. So let's talk about gene-based innovations. Things like CRISPR, that's the hot thing. I'll tell you, CRISPR's not so hot. We're now moved on. We have a lot more innovations that are coming out that are much cleaner, more efficient than CRISPR is. I love the story of CRISPR. Does anyone here know? It's yogurt-based. So they used to have these, all the big Europeans love yogurt. They eat a lot of yogurt, especially for breakfast. And they have huge yogurt manufacturers. And they noticed there would be certain batches of their yogurt that were more resistant to their endogenous kind of yogurt contaminants. And so they figured it out that it actually was because some of the yogurt strains, the bacterial strains, were resistant to a bacteriophage, which is a type of bacterial virus. And they uncovered this entire machinery, again, led to a Nobel Prize, called CRISPR. And so it's all based on kind of the yogurt industrial complex, trying to make as much yogurt as they possibly can. And they first discovered it in the bacteria, and then they realized, just like with the petunias and the RNAi, we all have this machinery in our body, and we're using it every day in order to change what we make and how we make it. So this is based on a machinery called Cas9. What happens is, similar to the RNAi, your body makes a guide RNA that binds to a place, it leads to a cut, and then it gets spliced together, which means it gets, I'm really bad at graphics, it gets moved together or spliced. I think one of the reasons that people aren't as excited about CRISPR is because it does do that double-stranded cut, and that's very kind kind of inflammatory for your cells. We don't like having double DNA cuts. It makes it more likely that it's going to combine in the wrong way. And so people are working, and you can also insert new pieces of DNA, so you can cut out an error and add in a new change. It's cheap and easy relative to other technologies. It's inherently pretty targetable. You can either remove or substitute new pieces of genetic information, and it's being used in Duchenne muscular dystrophy, it's sickle cell disease, thalassemias, Leber congenital amaurosis, transthreatin, like there are therapies which use this CRISPR technology. But the next generation is probably a much more exquisitely sensitive tweak on this, which we call gene editing. One of these forms is called adenine-based editing. There's also called prime editing, where what you can do is you can go in and you can flip just one base. So instead of causing that double cut, you can just change the one spelling mistake in one base and flip that out again. And those are likely to be moving into clinical trials soon. So hopefully this was a helpful primer that is both a call to arms as a community that we need some pieces in order to be ready for therapies, but also an understanding that there are a lot of different options out there in order to help our community. And what we need is the information to figure out which one is the right approach for us to take. And so we can help fix pieces of DNA, we can adjust how RNA is being made into proteins, and we can even replace proteins that are missing. So I'd like to acknowledge the Leukodystrophy Center of Excellence, which is where I work, and through which we run all of our BPAN-related work and our clinical team. I am part of a rare disease research consortium through the NIH called the GLIA-CTN, which is a clinical network of doctors that help children with rare diseases affecting myelin. And I want to thank all of you for allowing me to share today. You are the experts in this disease, and I just get to hang around you. So thank you, everyone, for your attention and time. I'm happy to take questions if anyone has any. I see you. Yeah, so the question was about the gene therapy infusion for the one video that we saw. That was one time. Gene therapy tends to be once. There's a lot of reasons behind it, but some of it has to do with our bodies don't like seeing a giant viral load twice. And that if we gave it a second time, there's a really high chance your body would attack the second infusion and break it down so it wouldn't be effective. Yeah, it's a really amazing story. This is what we're all trying to do.
More questions?
I always have questions. In yesterday's session specific to BPAN, we talked about the whole brain and the challenge in all of this that's giving so many of us hope, but this like barrier that's there. Can you touch on that a little bit again, just to like I'm just trying to remember the context of that, and I think it would be helpful for all of us.
Yeah, so I think the question, you had a microphone. I think the question has to do with how do we get the product that we make into the right places? And I agree with Dr. Hayflick that likely BPAN and many of the NBIAs affect a region of the brain much beyond just the basal ganglia or the places that the iron is accumulating. Otherwise, it wouldn't make sense that you would see developmental issues before you see iron accumulation. And you can see by myelination changes in the brain in a lot of different places. I think where I'm a little less certain is exactly what cell type I need to target. I know it's in a lot of different places in the brain, but each different approach gets into a different cell type with different efficiency, right? And I think that's one of the reasons people have originally gravitated towards the AAV therapy, because one of them, called AAV9, does a really good job of getting into the brain, but it doesn't get into all the cell types. So it may be incredibly effective with fixing the problem, in a cell type that isn't actually causing the disease. So I need something in BPAN and likely all the other NBIAs that reaches many areas of the brain, but I'm still not as certain on which cell types I need to be targeting. And so that's one of the avenues I think we'll be growing as a community, is understanding that.
Any more questions? No? Thank you, Sarah,
you, guys.
so very much.
Thank you, guys.
Up next, we have the disease-specific breakout sessions. So if you look in your program, you'll find your room assignments. Let's see here. We have BPAN is staying right in here. PCAN families are going to go next door to Ballroom A, where you were yesterday for clinicals. MPAN, you guys are going to the Westheimer room. That is just to the right of the registration desk, right across from the art in the hall. And then PLAN, you guys are going to be in the forum. Thank you. Hey guys, one more announcement real quick. Our Friday silent auction items that we still have available, they say Friday on the top, those are going to close at 5:30. That is directly before the memorial service today. Now, we were gonna close it a little earlier, but we made a mistake and didn't pick up pick up the clipboard. So we wanna make sure it's fair for everyone. So we're extending it to 5:30 today. And then if you think you won a prize, you can come back to the ballroom after the memorial service to collect your basket. Thank you. I'm done. Thank you, Meg.